Hello everyone, I'm Max and welcome to our 10th lesson, the asymptotes of rational functions. In today's lesson we will be primarily learning about the asymptotes, and where better to do that than on the functions where asymptotes are almost always present. Before we start, however, I have to tell you stuff about the Twitch VODs, as I said that I will be posting them in a separate playlist on my channel. However, I have had some issues saving them, plus I could not separate the music as the music got fused into the audio and certain songs were copyrighted. So I will from now on only save the VODs from specific events like the Among Us collaboration that I have planned, and there's a birthday that I'm invited to, and that stream will also be probably saved if I can manage it. I do not know how that's gonna work, but we will see. Also, I have made a Discord, linked as the first one in my socials part in the description, where anytime I go live or upload a video, hopefully, you can get a notification, plus you can hang out in our community and meet some other people, talk to me, because I try to be as active as I possibly can. I think I'm the most active out of all Discord servers in my own, even though I'm barely active, because I only use it on my computer, but still, if you want to socialize, talk, or be alerted by my new posts, go check it out. First link in the description in my socials, and let's get ahead with the lesson. So before we touch asymptotes, which is a joke that you may understand later in the video, we will learn what rational functions are and what makes them different from polynomials and power functions that we have learned so far. Well, a rational function is a ratio of two polynomials, which gives us a general formula. F of x is p of x divided by q of x. And of course, our p and q of x are both polynomials, and our condition is that q of x cannot be equal to 0, as we know that division by 0 is undefined. Here are 3 examples of how rational functions look like. I know this is a huge mess, but the option with all 3 graphs on the same coordinate system looked the most clear and least overwhelming, since the other option was 3 separate graphs, which may be a lot for some of you, plus they would be a lot smaller and harder to see. But yes, here we can see that the red graph starts on the left in the second quadrant, then drops towards y equals minus infinity, and then the very next x value, it keeps dropping from y is positive infinity, and keeps approaching some value as x approaches infinity. And if we look closely, it is the same value that it did not pass on the left as it started under it. This is an asymptote, but we will see how we get it in just a bit. Essentially, asymptotes are imaginary lines that the graph will never touch. That's where the joke, we will touch on that later, comes from. Now for the blue graph, it's basically the same way, but sort of mirrored and moved a bit, while the green one is all over the place. As you can see, it's falling down, barely curving, approaching x is 0, then out of nowhere drops from positive infinity on y, takes a turn and goes back up. So we see that there is a lot of things happening, as the graphs often break apart, curve dramatically, or completely level. That's thanks to asymptotes, and now let's finally see what they are. So as with every function, we have to cover its domain first and wholes, that way it's easier to understand it. Otherwise we might have a draft. To get back to the topic, the wholes happen when both polynomials are simplified and certain factors cancel out. But let's check it out on an example. Here we have a function of x squared plus x minus 2 divided by x squared minus 4x plus 3. We see that we can break these apart into a product of brackets, basically what we did several lessons ago when we learned how to solve equations and expressions. I hope you still remember Vieta's law, where we have 3 terms, ax squared plus bx plus c, and we need to find 2 numbers that when multiplied give us c, and when added together give us b. In p of x, which is how I'll be referring to numerators, so the top part of the division line. So in our p of x, our b is plus 1 and our c is minus 2, which is what we get from plus 2 and minus 1. So multiplying it together gives us minus 2, and adding it together gives us plus 1. So we write it as we learned, break it apart in the brackets. Now for the q of x, we have b as minus 4 and c as 3. We can get that with 2 negative numbers, as this one is positive and this one is negative. And the first idea that comes to my mind after so many number workings is minus 3 and minus 1, because you just multiply it and change the sign. And if you add them together, you see that we're right, so let's write it down as we did. Next, we see that we can cancel out x minus 1, and we're left with x plus 2 divided by x minus 3. But I will leave this bracket written as it is for a bit to show something. But first, let's check the graphs to see if they still look the same. On the left, we have the original one, and on the right we have the cancelled out terms. We see that they do indeed look the same, but let me tell you a little thing. The left one is not identical to the right one, and the only difference lies in a single point. And that is not a lie. That is true. There is exactly one point that differs. That point is 1 minus 1.5. Or to clarify, at x equals 1, the single point on the red one, of course, the green one has it, the red one does not. That point here is not defined, but it approaches the y value of 1.5 from both sides. This would be great introduction to limits or continuity, but for us now it is enough to know that this is called a hole, a single point that is undefined, while the rest of the graph approaches that value that the point would occupy. But let's see why the point is undefined and why the graph still has the shape like if it were defined. As you can see here, this is the graph and this one specific point is undefined. To see that, I will insert the values of 1, 0.9 and 1.1 into the original equation, and then insert just x is 1 into 1 where x is 1 is cancelled out. There's a lot of 1s. But yes, I inserted the numbers into the equation. So I solve the top and the bottom half, I get 0 divided by 0, that's undefined. That was to be expected. Next we put in 0.9. We get a value that is slightly greater than minus 1.5. As in greater, that's closer to 0, because it's negative numbers. Absolute value may be lower, but in general it's greater because it's a negative 1. And then when we put 1.1, we get slightly lower than minus 1.5. And we see that since 1 lies between them, the value of this one should lie between them as well. Now to get the simplified formula that I said I'm gonna put 1 in, to see what value does this even approach, we put in 1, when we get 3 divided by minus 2, we get minus 1.5. So we see that holes happen because we cancel out, because there is a factor that can be cancelled out. That factor on both sides, so the denominator and numerator, that bracket equals to 0 at the same x, which makes the entire function be 0 divided by 0. And when that cancels out, the function is defined in that point. So the easiest test for holes is to see if you can break the function into factors and cancel out on both sides of the division line those that are equal, aka would make the function equal 0 divided by 0 at a certain x. As for the domain of the function is all real numbers without the values where the denominator, so the q of x, equals 0. Since that is where the fraction is not defined, as not all, it's important to clarify that not all points where q of x is 0 are holes, only the ones where the same x is also a 0 on the p of x. I hope we still remember zeros are when you get y equals 0 for a certain x in a function. And we could write our domain like so, replacing the x with the value that gives us a 0 from q of x. So in this specific case, we could write this as df equals r minus squiggly bracket 1 end of squiggly bracket. Now we can finally get to the asymptotes. Before this, I mentioned that holes happen when both p of x and q of x have a term that is equal to 0 at a certain x. So, when we have a function result of 0 divided by 0. But when only q of x equals to 0, we get a vertical asymptote. That is a vertical line that the graph will always get closer, but will not be defined at the exact x that the line occupies. Meaning that if the asymptote is on x equals 2, the graph will approach either infinity before x equals the asymptote and drop from either the same or the opposite infinity depending on the degree of the 0. Since we know that if we had a single function that we factor like that, each bracket would be a 0. So I will refer to these values as zeros of the denominator or numerator. So vertical asymptotes are zeros of denominator that are not also zeros of the numerator. So if it's a 0 at the bottom, but not the 0 on the top. If we have a 0 that appears an even amount of times, like in x squared, so 1 over x squared, that is an even 0, meaning that the sign of infinities does not change. Meaning, if the graph approaches a positive infinity, it will drop from the positive infinity after that x. However, if we only have an odd number of zeros, like in n over x, or x to the power of 3 for q, we would change the signs, so approaching the negative infinity, but continuing from the positive one. To clarify, here n refers to 1 on this example graph, but I set n as it can be any polynomial, as the vertical asymptote is unaffected by it, unless the same 0 appears in the p of x, where this would become a whole. But here we just assume that it doesn't, so we can show our point. So to find the vertical asymptotes, you first find the zeros of q of x, then find zeros of p of x to check which of the q of x zeros are actually wholes, and which are vertical asymptotes. Now I can tell you this as I have observed these functions. The 0 in p of x, we will learn that that's a 0 of the function, so that's when it crosses the x-axis. And when it's a 0 in the q of x, that means it's an asymptote, and it approaches infinity and then down. So if we were to approach the 0 from up and from down, we would have these lines somehow going down, 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 making it more straight, closer to each other, at one point touching each other, and then touching the x-axis at wherever the 0 is defined. So in this case, that's an x equals 0, in some other case it would be x equals 1. And then the same logic, so for even and odd zeros, if it was like this, they would create a tiny m. If it was like this, it would give us a sort of x to the power of 3 shape, in this close proximity, of course. But then it continues on straight, so that's more of a root function, which we will see later on. But now that we have mastered the vertical asymptotes, let's check the second type, horizontal ones. Horizontal asymptotes are not the zeros of p of x, as I said before, those are the zeros of the function. They are the points where the graph intersects with the x-axis. Horizontal asymptotes, however, are the y values that the graph approaches as x nears negative or positive infinity. Using this information and what we have learned last time, that the behavior of the graph as x increases is determined by the leading term, we will use the same logic, which gives us 3 possibilities depending on the degree of the leading terms. So let's make a table. Oops, I made a double jump, but yes. So to determine which of the 3 situations we're in, let's compare the degrees of p of x and q of x. The degree of p of x will be marked as n, and that of q of x with a j, to make it easier for you to hear it, as usually it is m and n. But they sound basically the same if I say them, so I'm gonna be using n and j, plus I'll keep this here so you can always refer to it. First comparison is when n, so the degree of p of x, has a lower value than the j, which is the degree of q of x. In this example, the asymptote is the x-axis, so y equals 0. The graph does cross it sometimes, but the asymptote is defined when the x approaches infinity. So until that, it can cross it, just like converging alternating series and sequences that went above and under a certain value, but they did approach it. Next comparison is when the degrees are the same. Then we look at the ratio of the leading coefficients. So the leading coefficient of p of x marked as apn divided by the leading coefficient of q of x marked as aqn, although usually they're marked as an and bn, but I just used p and q here to make it more clear, because introducing a new variable would just confuse them more. Here we will take the ratio of the example, like here, and we get 2 divided by 1, so the leading coefficient is 2, and the leading one down here is 1. So our asymptote in this case is y equals 2, which here I now see is kind of hard to see exactly because I zoomed out too far. But if it's not clear enough for you, you can always graph it on Desmos. I always say this, that following along on Desmos or on paper is amazing. Plus I gave you the graph here, so you can also check for yourself how it behaves. You can zoom out to the infinities to see if it actually does approach it. But yes, putting it in from your own experience is the best way of learning. And now for the third and the last possible comparison, where n is greater than j, so the degree of p of x is greater than the q of x. This is where we will use what we have learned last time, the division of polynomials. So this example does not have a horizontal asymptote. However, once you divide p of x with q of x, you will get some k of x and r of x. K of x is the formula for the asymptote, and r of x is only useful to determine where the graph itself, so the function, intersects with the asymptote, because asymptotes only work when x approaches infinity. As you can probably imagine, that means they are going to be diagonal or even more complicated, like square, cubed, even further powered up. But do not worry, I will only want you to know the linear ones, as they are the only thing that may be on the mini test, so do not worry. Even though I may show an example that does not have a linear one in it, I do not expect you to know it. Then about the remainder, as I said, we usually ignore it, but if you need to know for sketching or for theoretical questions, this is the only use for it in this case. Here is the example of an asymptote that is not linear, so the green light is the asymptote and the purple is the graph. You can see that they touch in the point 0, 0, but then it keeps approaching it as x approaches infinity. So, an oblique or slant asymptote is the last of the three asymptote types that we will cover. And unlike how I mentioned in horizontal asymptotes, that one that is remaining takes the shape of the result from division of the two polynomials, with oblique or slant, we will only focus on the linear ones, so only the ones that are described with the linear equation in a form of y equals kx plus n. To get its formula, we have to do the long polynomial division. We take the kx, ignore the remainder, that the k of x equals to y and gives us the formula to sketch it. Here is the general formula, so the degree of the numerator has to be exactly 1 degree higher than that of the denominator. On the example here, x squared divided by x plus 2, if we do the long division, we will get our k of x as x minus 2, and we ignore the remainder. So let's graph out the function, and then k of x as the dashed blue line. We see that the blue line is a linear function, and the red one approaches the blue one as x increases or decreases, so getting closer to the infinity. We see that we will need to bring out our polynomial division skills to make solving these tasks a lot easier on us. Now, I wouldn't really go into graphing, as for most of you that would be completely useless, and those who really want to learn should practice on their own as much as they can, but a little guide wouldn't hurt anyone. This may not be the steps your teachers told you. This is just how I approach it, and it may help some of you understand it, as we approach it like building a house. Make the plan, set the ground, place the foundation, get the pillars and everything, mark all for the walls, fill it in, then decorate. This is a severe oversimplification, but it does show an example. First step is to determine the domain of the function, so to see which ground, so which x values we can actually put in, meaning we find which x's we can't put in, and that's the ones where q of x equals 0. So we take it as a separate equation, solve for zeros of the denominator polynomial, and those x values will remain empty. Then we check the zeros of each of the polynomials. So to find the graph zeros, we find the zeros of the p of x, so numerator. That's for our graph crossing the x-axis. Then to find our vertical asymptotes, which is only when q of x equals to 0, then we find the holes, that is when 0 is present in both polynomials. We sketch the asymptote with dashed lines and mark any points we know, like zeros, on the coordinate system. Next, we check the relationship between the degrees of our polynomials and set the horizontal asymptote accordingly. So, remember the table. If the degree of p of x is lower than the one of the q of x, we have a horizontal asymptote at y equals 0. If the degrees are equal, the asymptote is at y is the ratio between the leading coefficients of the two polynomials. And if the degree of p of x is greater, there is no horizontal asymptote, and we have a slant or higher powered asymptote, which we agree that I'll only give you examples of linear ones. So we do have to determine the oblique asymptote. We just have to get the result of the division and ignore the remainder. After that, we will plug x equals 0 into the function to see when the graph intercepts the y-axis, and we also mark that on the coordinate system. If we haven't yet, we plot all the points and asymptotes accordingly, but it's always nice to do it as you're going so you never forget stuff. Next, we have to predict the behavior near asymptotes, One way is by inserting random x right next and right before and right after it, and seeing where the y falls compared to the asymptote, then trying to sketch the graph. After that, you just check if all the asymptotes are in the correct relation to the graph, and if all the holes are marked right. There is usually one more step, which is to take a derivative to find where the turning points are, like the vertex is in the quadratic function, but since we haven't done that, we will just wait until then to learn it, and we will just rely on rough sketches. Here is our example, so let's go through all the steps and determine how we would graph it. We have x plus 2 divided by x minus 1, so our domain is all real numbers except for 1. And since we see that when we put in x equals 1, we do not have a 0 divided by 0, so this is not a hole but a vertical asymptote, and we would mark it something like this. Since it is an odd 0, which means there is only one type of bracket that we would put in the value and gets a 0, the asymptote will change the signs, meaning that if one side is in positive infinity, the other one will continue from the negative infinity, so let's remember that for the time being. After that, we find the zeros of p of x to see where the zeros of the graph will be. That is, at x equals minus 2. Next, we check for the horizontal asymptote, and since the degrees are the same, it will be y equals 1 divided by 1, as that are the leading coefficients, so y equals 1. Now let's check for y-intercept, so the point where the graph crosses the y-axis. That is when x equals to 0, and we get that when we put in the numbers, so 0 and 0, we get plus 2 divided by minus 1, which is minus 2. So the point is 0 minus 2. And it's finally time to sketch it. Now we have two asymptotes and 2 points, which allows us to make a curve that would look something like this, and where we make sure to show that the curve approaches the asymptotes, goes through the points, and then finishes off again as the asymptote. I do apologize for horrible sketching skills. It is very hard to draw with a mouse on the PowerPoint, but yes. Now since this graph still has x greater than 1 in its domain, we have to figure out how to sketch that. And to do that, we have to remember the vertical asymptote. It is odd, meaning that the sign of infinities will change. So if one side is going to y minus infinity, after the asymptote, on the other side it should fall from the positive infinity. And if with increasing x values, the graph has to approach the horizontal asymptote, we can basically mirror what we already drew. So this is how I would sketch it. Well, maybe a bit better if I drew it by hand, but I hope you can see how this works now. And to finalize it and see if we did it right, let's compare it to an actual graph. We see that we actually did quite a good job. Well, aside from the lack of steady handwriting, we did great. Perfect. We did it amazingly, and now off to one last example before the mini test to see how well you actually learned. So we take the domain, which is all real numbers without the number 1 again, and we know that this is a vertical asymptote or a hole, and that it is odd, meaning that the signs will change around it if it is an asymptote, or do a tiny change if it's a hole. I will mark it as if it is a asymptote, so it is easier to mark the exact spot later. Although now that I think of it, it should be better if I use the dotted lines, because it's a separate marking, as you will see on the mini test. Now we check for zeros. The 0 in q of x is 1, which is a vertical asymptote or a hole, which we can only find out if we take the zeros of p of x, which is a quadratic equation. And if you also remember the formula, the minus b plus minus the root of the discriminant, that is divided by 2a, we will plug in the numbers and we get minus 2 and minus 1. So those will be our zeros, meaning that our q of x0 is really an asymptote again, because the p of x zeros are the zeros of the graph. Now we have 2 points and an asymptote. Time to find the horizontal or oblique ones. Since we see that the degree of p of x is greater for 1 power than that of q of x, we will have no horizontal and 1 oblique asymptote. Now I will let you guys divide to practice this, and when you're done, you can unpause and see if you divided correctly, as I think covering it in the last video was covering it enough. Now that you hopefully paused the video, solved it, did the division for yourself, and unpause it to check up. If you did, you got the k of x that equals to x plus 4, and the remainder is 6, meaning out our oblique asymptote will have a formula of y equals x plus 4. And we will fit in our graph like so. And now that you have hopefully done the division, if you did, you get this. Now there is just two more things to do. Find the intersection with the y-axis and sketching it. To find the intersection with the y-axis, we put in x equals 0, and we get 2 divided by minus 1. So again, the point is 0 minus 2. If I connect the points and follow the asymptotes, I would get something like this. And since this covers roughly half of our domain, let's fill the rest of it. Now to fill the other half, we have to remember that we have an odd vertical asymptote, so the signs will change. Meaning, this one goes to negative infinity and continues from the positive one. So if I complete it, it would look something like this. Now let's compare it to the real thing. We see that I did quite well. There is 2 points marked here for the turning points. So the center one here between the 2 zeros and this one. We could only pinpoint them exactly if we knew how to get the derivatives, but I will save that for a later lesson, as our sketch was very accurate nonetheless. I mean, this is y equals 10, this one was slightly lower, this one barely curved over, so I think we did quite good. That's it. For today's lesson, it seems like it's a shorter one. But yes, here is the mini test. I wish you best of luck solving it. There is a couple of things I do have to say. I do recommend joining my Discord server, so that's a easier way to ask me if you have any questions regarding mini tests and everything. I can help you learn stuff. We have a whole less channel dedicated to solving homeworks and teaching each other, and we're building a very nice community. Plus, I am chasing affiliate on Twitch, so it would mean a world to me if you drop by on my live streams, which are Tuesday and Thursdays, 5 PM London time. It would mean a lot if I got that affiliate by the end of August, because that's the end of my streaming time. After that, I go back to university and I will only continue making the videos. But yes, I wish you best of luck on the mini test, and I'll see you all on our next quest. Bye!